Howdy, y'all. So today I'm going to be talking about how to write shellcode for very small embedded systems. And we're going to be dealing mostly with 8 and 16-bit embedded systems, which means that none of these has enough memory to run calc.exe, which means that none of your existing exploits are going to work. The topic itself is one of those things that's more like a conversation that you would have later in the night of drinking, because when you're drinking and you're talking about hacking, it goes through two phases. And the first phase is that you talk about some cool thing that you hacked. And the second phase is that you talk about the individual pieces of the hack that made the exploit itself interesting. And I'm in a bit of a bind because the majority of the talk is going to be of that later style, and I still need something flashy to have good pictures. So I'm going to have a little sidebar here. In 2010, I was here in Amsterdam with two friends of mine, and we decided to build an art exhibit. If you've never had the opportunity to pretend to be an artist, I suggest you take it. It's a shitload of fun. This here is the opening kiosk for multi-threaded Banjo Dinosaur Knitting Adventure 2D Extreme, which is an RFID video game that we made in an art museum called Mediamatic Bank that used to be not that far north of here. The player begins by showing up at this kiosk and tapping a Dutch Metro card over the heart, and then drawing on the screen a sprite. The sprite is then used in a video game. The video game is controlled by RFID tags on these arrows that are at the front of the table. But there's a complication, which is that the RFID readers can't handle two cards at the same time. And both players have to share the same set of arrows. So you and I, if we were playing, could not both move left at the same time. You could move left as I moved right, but we could not move in the same direction at the same time. So you get to see how well people at the museum knew each other. So like strangers are ever so polite. You know, if these two were strangers, then the man would say to the woman, "Excuse me, madam, but might you please cease moving left such that I might move left, as that would be amenable to my desires at this moment." But in fact, these two were newlyweds, so he thought that he could just brush her hand out of the way ever so politely. And what she did was she picked that beer up and she dumped it on his head. But it can't be a knitting adventure, at least an extreme 2D knitting adventure, unless you have an actual knitting machine involved. So we hopped in a van and drove to North Holland singing the A-Team theme song. We didn't know the A-Team theme song, but we didn't let that stop us. And when we got up there, we bought this knitting machine. This is a photograph with annotations of the keypad. Previously, a Tandy Radio Shack Trash 80 floppy disk drive emulator had been written in order to make fake floppy disks for this knitting machine. But you had to type in dozens of commands in order to load a new pattern. And we wanted to be able to load in patterns quickly enough to do a high score list as a tapestry for the video game. So what we did was we took the keyboard apart and then we reverse engineered which row and which column were connected for each button that were pressed. These are the annotations for the rows and the columns. And by touching the right two together using a paperclip, you could actually press a button on the keypad. We then built this Arduino shield, which allows you to connect the rows and the columns electronically by an order that's given from the video game computer itself. So the table that we had on the first slide that plays the video game, that was actually tied directly into the keypad of the 1980s knitting machine, allowing it to load and to dump out a high score tapestry. And that was how our Banjo Dinosaur had his knitting adventure. If you want to do things like that at the simple end, if you're just going to wire up an Arduino and press the buttons as they would be pressed by a person, then you don't really need shellcode, and you don't really need any advanced debugging techniques. We were able to do that entire project by doing nothing more than using a multimeter and the sort of hobbyist-grade equipment that you would expect in a recently formed hackerspace. But if you want to do something more sophisticated, then you need shellcode, because you need to dump a copy of firmware, and quite often these devices are locked. When you're working on a PC and you're used to the 32-bit world, you sort of take for granted that you can get a copy of the code that you're reverse engineering, or you can get a copy of the code that you're exploiting. When you can't, it's because of something like ASLR that's just scrambling the position of the code while the contents and the meaning of the code is something that you can already view and understand and reverse engineer from your own copy. So in this lecture, I'm going to be discussing the different tricks that are sort of unique to embedded systems, and the tricks that, if not unique to embedded systems, are at least different in embedded systems from what you would see in the host. I'm going to show you how to exploit devices that don't allow you to execute code from RAM. I'm going to show you how to exploit a device by overwriting flash memory piecemeal instead of as pages. This allows you to patch the flash memory in the raw, even if you need to use the page that you're patching in order to continue running your exploit. The majority of this came from exploits that I've written for clients and from discussions that I've had with Aurélien Francione he's now at Eurocom. We wrote a paper a few years back called Half-Blind Attacks, Masked ROM Bootloaders Are Dangerous. And in this paper, we actually constructed a very short return-oriented programming exploit blind, in that we didn't actually have a copy of the firmware from which we were building our ROP chain. And also from conversations that I've had with Sergey Bratis and some of our work in embedded systems security. So kind thanks are due especially to them. So when you're exploiting a PC, you sort of take for granted that you have an operating system. You take for granted that you can do interrupts in order to call the operating system, that you have a libc that is loaded into memory. On embedded systems, a lot of these features are lacking. You don't really have dynamic libraries. You do on the higher ends, but in the 8 and 16-bit realms, you don't have them at all. So your operating system and your application and all of your libraries are statically linked into a single executable. If you have a libc, it doesn't have anything useful in it, or terribly useful. You won't have anything like the system or exec functions. So you have to build your exploit from smaller pieces, especially for return to libc and return-oriented programming attacks. The defensive features are there, but they're there by accident. So on a PC, you'll have ASLR in order to prevent an attacker from knowing where pieces of the target are. But that's done explicitly as a defensive feature. On an embedded system, you're still in that position of not really knowing where things are, but it's not the defender trying to protect himself from you. Instead, it's that the firmware image is locked and you're not allowed to read it because you don't yet have a shell on the box. There's no execute bit, but instead you've got Harvard architectures. And in Harvard architectures, you have separate memories. So there's no such thing as having a pointer. You have a pointer to code, a pointer to data, a pointer to internal RAM, external RAM. You have all of these different regions of memory, and they don't overlap, and they're not always mapped on top of each other. Some of these architectures have, well, all of them have instructions for reading and writing RAM, but many of them do not have instructions for writing to code memory, because they just assume that it's going to be a permanent ROM. And so as they've been extended to support things like flash memory, that's all done in very strange and very device-specific ways. So there are lots of weird registers and custom code and architecture-specific techniques that you need to learn when reverse engineering these devices. One of the chips we'll be dealing with is the Intel 8051 architecture. This is more popular than x86, AMD 64, and ARM combined. Every one of you has at least one 8051 on your laptop. You probably have several in your cell phone. And this is a very old design. Intel no longer makes the chip, but all of their competitors have cloned the chip. And you'll find this as helpers in all sorts of small devices. If you have a Seagate hard disk, there's an 8051 that's used just for the read-write head. And this is in addition to the ARM chips that are elsewhere. It's Harvard architecture, so you have many different memories. And it's a rather old Harvard architecture device, so it only has 256 bytes of internal RAM. This is called data or iData. You have X-data, which is a separate region for external RAM. And this was because they assumed that the chip itself would have very little RAM inside of it. The 256 bytes would be the most that they could fit. And for any more RAM, they would have to go to an external chip. RAM and data and code are completely separate in the original 8051 design. So when you have a pointer, that pointer means something different, whether it's a function pointer or a data pointer. The same number can refer to two different things based upon the instruction that dereferences it. Instructions are byte-aligned, and there are thousands of different clones of this chip. So everything I've told you about this chip is wrong for at least one of them. Some of these devices cause code and data memories to overlap, and on those devices you can execute from RAM. Other devices have a primitive MMU in them, so you can actually move regions of memory around, and this is how they get around the 16-bit memory limit. Because pointers in this device are only 16 bits, and you can't do that much with 64 kilobytes of memory. They can swap pages in and out, and you do this by setting a register. The 8051 is used in this device. This is a turning point response card RF. The company that makes this really likes to make legal threats. But they also really don't know how to protect their code. So you can take this device and you can just read the executable code out of one of the memory chips. If you look at my blog, you'll find an article on how to reverse engineer this device. The secret number that they threatened to sue me for releasing was in hexadecimal 0x12, 0x34, 0x56. So be careful knowing that number. This is a photograph of the radio plus CPU that's inside of this device. And the vulnerability arose from them needing both a microcontroller and a radio in the same chip. You can tell that this is a radio because of those square inductors on the bottom left and the circular ones just a bit above them. When you add radio to a chip that previously didn't have it, it's easy to combine radio and digital circuitry. It's also easy to combine flash memory and digital circuitry. But it's very difficult to combine flash memory and radio. So in this chip, they weren't able to fit the flash memory on die, and they had to include it as a separate package. So you could just separate the memory chip from the rest of the board and read it. And that gave you your firmware dump. The second device is the Girltech IM-Me, and this is a children's text messaging toy that allows you to send and receive text messages with your friends through the internet. This was manufactured just before the year hit when every child on Earth had a cell phone. And in the photograph, you can see that we've replaced the firmware on it. So the command console in the upper right is actually ordering one IM-Me to hold a carrier wave on a frequency. And the IM-Me in the background is running a spectrum analyzer program that Michael Osmond wrote. So the radio in this device can be hijacked as soon as you're executing your own code on it. We also have firmware images for reflexively jamming APCO P25 police radios that are used in the States and Australia. And you could easily build jammers for other protocols. And you can do this as soon as you get code execution on it. And it doesn't matter that it's just a toy. This is a chip related to the one in the Girltech IM-Me. This is the ChipCon 2530. The IM-Me uses the ChipCon 1110. But both of these have an 8051 core, and they both also have a radio, and they're in the same package. And unlike the turning point device that I showed you, this device has a protection fuse. So it can protect itself in order to prevent its firmware from being dumped. If you want to reverse engineer the firmware of this device, you need to come up with an exploit that allows you to dump the contents of flash memory. And in doing this, it's often helpful to use memory corruption exploits, but you won't have a copy of the firmware as you do it. So this gets tricky. The MSP430 is the first architecture that I really got to know. It's kind of like the PDP-11, except that it has more registers and a few features removed. It has 16-bit aligned instructions with immediate values following them. And it's von Neumann, so you can execute code from RAM. There are security-enhanced versions of this that do not allow you to execute from RAM, and we'll get to those later on. This is the Face Dancer. It's a recent project of mine that uses the chip. This board allows you to write a USB device or USB host in Python on your workstation. But as far as the other device sees it, it's just a regular USB device or a USB host. So there's a Python script that you can run through this board to make a fake disk or to make a fake keyboard, a fake mouse, a fake serial port. You can make a fake uninterruptible power supply, wait for Linux to automatically load the driver, and then order the computer to shut down by telling it that its power is going away. When you fuzz device drivers this way, you come up with all sorts of vulnerabilities. But you might want to go the other way. You might want to infect a USB device or to dump a USB device's firmware in order to find a vulnerability in the device that you can exploit. And that's where the techniques of this lecture become handy. This device also uses the MSP430. This is the Spot Connect. I've done a lot of reverse engineering of this, and there were a few papers that preceded it. This device is really neat because it's a Bluetooth to satellite transmitter. So your cell phone connects to this, and then you run an app on your phone which orders this device to transmit up to a low Earth orbit satellite constellation. And from that satellite constellation, it gets relayed to the internet, including your GPS coordinates and a short text message. This will also transmit on emergency broadcast frequencies so that if you get stranded or if you break your leg in the woods, you can use this to call for help. But when this transmits through the satellite, it's completely clear text. And if you could replace the serial number of this device, if you could send your own packet in the raw, you could easily impersonate another device, which would allow you to, say, have 10 of these in the same subscription plan. Or to create a fake message from any device that you were able to sniff in the wild. And the over-the-air protocol is completely clear text. So if you can find any one of these, at the very beginning it includes everything you need to impersonate it. And this is the Next Hope badge, which was a hacker conference badge that I made in 2010. This can be reprogrammed to emulate a Microsoft wireless keyboard. And thanks to a vulnerability published by Max Moser and Torsten Schroeder, it's known that those use a magical form of cryptography called exclusive OR, and that the 5-byte key is the MAC address, and that in every key up event you have 13 bytes of zeros XORed with that key. So you've got the password all sorts of places in that packet in the clear. You can feed that right back through and then begin typing on the keyboard of anything near you. By replacing the firmware of this device, or of the turning point clicker that was a few slides back, which uses this compatible radio, you can emulate the keyboard, and you can even make this exploit standalone. You could have it so that just by walking around with this badge, Microsoft keyboards around you would start loading up the Rickroll video on YouTube. And this is the MSP430. This is the 2274, which we use in some of the smaller good FETs. And you can see that this is divided up into different regions. The niftiest region, it's down in the middle. I don't think that you can see it on the screen, but this is it zoomed up. In the microscope, it looks kind of like a tablet with Egyptian writing. And you'll notice that it's divided into 16 columns. You'll also remember that this is a 16-bit chip and has 16 bits of significance in its address bus and its data bus. And you'll note that there are little dots as you go up and down it, and that the dots vary by frequency in certain regions. And if you zoom way in, you'll recognize that each dot is either there or it's not there. These are bits, and you can read them visually. This is what's called a mask ROM. And a mask ROM is nice because it's written as the chip is manufactured. So Texas Instruments wrote this mask ROM, and it doesn't matter whether this chip ships in a Turning Point product, or in one of my products, or in the Spot Connect product. This Mask ROM is always there unless you pay a lot of money to special order chips without it. And when it's included, even though you can't do a return to libc attack against the C library because you don't know where anything is, well, you can return to the boot ROM. And what this ROM does is it's a recovery ROM for flashing the chip when it's been misflashed. And this contains a complete bootloader. So this allows you to get a command console on the chip. It has code to read all of memory. It has code to write memory. It has code to change the clock settings if you need to speed the chip up or slow it down. And the only protection that this offers is that before it will let you do anything, you have to enter a password. And the password is the last 16 bytes of flash memory. It's the interrupt vector table. So 16 words, 32 bytes. But if you can skip that password check, or if you can find a bug in the password check, then you can jump into the mask ROM, and you then have a command console that will tell you how to use it will allow you to read and write the chip. And by dumping the code out, you then have the keys to the kingdom. You can read any keys that are in the chip. There's nothing else in this chip that allows you to keep a secret after this password protection has been bypassed. You also have AVR chips and PICs. AVR is what's used in the Arduino. A PIC is used in everything. There are satellites running PICs. God help us. There are also all sorts of architectures that are sort of split off from things that were popular in the 80s. So the 6502 and the 6805 and the 68000, all of those still exist in embedded systems. You'll still find Z80 chips, like you had in the Texas Instruments graphing calculators. And these still ship in modern products. They're just sort of hidden away, and they're the smaller chips. But they're still worth attacking because this is what gets you direct control of a radio, or a satellite transmitter, or a smart meter, or any of the other small computers that you might want to attack. This is a picture of the Atmel. You'll also find artwork on these chips. This is the AVR logo. The French MetroCard, the Navigo, has both a frog and a snail on it. And it's manufactured by a French company, so I'm not sure whether it's a joke against the French or a joke by a subcontractor. This is a photograph of the PIC microcontroller. As I mentioned before, on a PC, our goals are pretty clear. We either want to load malware onto a desktop, or we want to drop a shell on a server. And that's the goal that we're after. On a microcontroller, our goals are very different. Generally, we want code. Sometimes we want keys. So when you're using an exploit to dump the firmware, you kind of have to know what's already there, or at least where things will pop up. If you're trying to dump the application firmware, then you rely on the bootloader in order to be the target that you're exploiting. USB bootloaders are lovely because they have complicated parsers in order to handle the USB commands. And wherever you have a complicated parser, you have an exploitable vulnerability. There's also the case that a peak primitive, if you just have a bug that allows an info leak to the outside of 1 byte of memory that you can do reliably and repeatably, that's almost as good as complete code execution. Because as the attacker, you don't have that much memory to exfiltrate, and you can generally try as many times as you like. So if it takes a few hours for the exploit to run, or a few minutes, that doesn't matter. As long as you get a copy of the code and a copy of the keys, you have everything you wanted out of it. There are also some strange uses for exploits. I was working on a project with some friends of mine at Eurocom in France, and we needed to write a backdoor for a device. Now, getting foreign code into the device was no problem. The updates weren't signed. The trouble was that I wound up with a stack from the floor to about here of these devices that I bricked by loading bad firmware images. And once I bricked them, they were permanently bricked. We never found a way to unbrick them. So we wound up using a stack memory corruption exploit, not to get code execution for its own sake, but to get temporary code execution by only tampering with RAM. And by only tampering with RAM, we were able to inject our foreign code without having to worry about bricking the device. because we knew that everything was temporary, and as soon as we flipped the power switch, it would go back. And this gave us a development kit for writing our backdoor. Quite often in these things, you're trying to build a development kit for doing further work than your target. It's also useful for upgrading unpatched firmware. I had a company call me up, and they said, hey, we heard that you can write an embedded exploit. I'm like, sure, what do you want to hit? And they said, well, we want to hit our own product. What happened was that they forgot to leave in a space for upgrading firmware, and they had a bug that they really needed to fix for their customers. So their choice was to either recall all of these physical units, or send out technicians to replace all of them, or they could use a remote code execution exploit to inject a stub that would load the rest of their new firmware and fix things. The version that they wound up smuggling in did include a firmware update feature, so it was no longer necessary to do this. But you need to get used to the idea that in embedded systems, you might want to exploit something or to reverse engineer it for a much stranger reason than you would have on a PC. It's also the case that these embedded devices very rarely have credit card numbers or email. So the two big targets are out. When you're exploiting the 8051, it's an 8-bit CPU and it's Harvard architecture. So on most variants, RAM is not executable. There are dozens of clones, though, and each of the clones has its own special features, and it's these features that you have to look at when writing your exploit. For example, because it has separate memory spaces, the big ones are code, data, I/O, and X-data. Data is the 256 bytes of RAM that, when this was sold as a single chip in a physical package, would have been the ones inside of the package. And then all of the code memory and all of the extended RAM would be on external chips on a separate memory bus. So you have 64 kilobytes of space for code, and you have a separate 64 kilobytes of code, memory for X data. But these two don't overlap, usually. By the original design, these would contain separate things, and you could have a pointer that would be the same in both cases, but depending upon whether you used the move instruction or the move C instruction, it would mean different things. And this architecture is everywhere. You'll find them stuck inside of FPGAs, stuck inside of ASICs. Wherever a designer of a chip needs to throw in a microcontroller and doesn't really care about the performance, he'll use an 8051. They're cheap, there are open source hardware versions of them everywhere. So modern chips have exceptions, but they have exceptions for weird reasons, and a lot of it has to do with needing to self-reprogram. The original 8051 could not write to its own code memory, so the designers extending the platform had to come up with a way to allow that. So with chips that have too little memory, they just unify the address space. So if the sum total of your RAM and your flash is less than 64K, a modern design might just put them into the same address space, and then you do have a pointer that works like a von Neumann pointer. And they can do this without changing that much of the rest of the instruction set. The only thing they have to do differently is to tell the linker that data memory begins at a different address, and that's just a linker flag. For codes with lots of memory, what they do is they have a primitive MMU that allows them to choose a sort of moving window within their 64K region. This is kind of like segments on 16-bit x86, except that instead of moving the RAM for different purposes, they just sort of move the window for everything. Now, when you're writing to flash, which is particularly useful if you can't run from RAM, there's no standard instruction for doing it because flash memory didn't exist when this architecture was made. You could use multiple calls to a poke primitive, but you have to make sure that you know everything that's going on in the clocks. You have to make sure that you can do this reliably in a loop, and you need to do it without native code, and you might have to do it without certain pieces of code ever running. So the options that work vary by architecture. And these self-reprogramming features are sort of a loophole around these limitations. If the chip crashed every time you tried to fetch an instruction from flash memory while programming flash memory, then the architecture would be hell to write a self-reprogramming program for. So the loopholes that they wrote in, one is that they map RAM into both data and code. And if they do that, then you can execute from RAM. So you just run from RAM while you're writing to flash memory. A write to flash memory is rather traumatic, and while you're writing, you can't read. The other way is to just have the flash memory return back a jump that bounces back to itself. This is what the MSP430 does. So if on the MSP430 you start writing to flash memory or erasing flash memory, then for that entire write or that entire erase, which takes many instruction cycles to perform, you can't read from flash memory. So what it does is it gives you back the constant 3FFF, which is a jump back to itself. So the CPU stalls, and it keeps stalling until the write is complete, and then it drops right back to the instruction that was at the address that it tried to fetch. As a bug, this will mess you up if the CPU is trying to fetch an immediate value instead of an instruction. And the third trick is that mask ROM is used to copy X data into code. And this is because mask ROM is separate from flash, and mask ROM will work while flash is being written to. Now you can exploit these. So if RAM is mapped into both X data and code, then you can just return into it, and this becomes a 1996 style smashing the stack for fun and profit attack. If it gives you the jump to -1 when busy, then it's harder to exploit because there's no gadget that just writes flash. But if you get a poke primitive, you can sort of construct a very slow one by individually poking the special function registers that handle writing to flash. Special function registers are like I/O addresses on a larger machine. You write to them, and that goes directly to a peripheral device. In this case, the flash memory controller. Now, if there's mask ROM that copies code from X data to code, then this becomes a lot easier to exploit, especially because the calling convention is usually documented. So you know exactly how to set up the stack to call a function that copies from one address to another. Later in this lecture, I'll show you how to overwrite flash memory without erasing it in order to patch individual bits. And combining the two is helpful. Now, when you get your shellcode in, you need to speak to the outside world, but you quite often don't have enough room in which to do it. So one of the exploits that I wrote involved a vulnerability in a USB bootloader. Now, the exploit would only be useful if I could dump a copy of flash memory and RAM. The purpose of this was to use the bootloader to dump the contents of memory. But I had to do this through the USB protocol, which has very, very small buffers. It's 64 bytes per fragment. So the first stage shellcode needs to be really small. I could call back into the USB stack, but that's too complicated. And I could call into, say, the serial functions for talking over a regular serial port, but the serial port gets disabled when the USB port is enabled. So to simplify it, I realized that the LEDs were always active. And the LEDs are just on a general purpose I/O port. And a GPIO port usually has a configuration register, an output register, and an input register. And when they're configured for output, you can just write to the output register, and if you write a 1, then the pin goes high, and if you write a 0, then the pin goes low. So you can blink the LEDs in the correct pattern to dump a copy of all of the firmware. Several people have done this trick, but the first time I found out about it was from this book, Journey to the Center of the HP28. It was published in 1990, and they didn't have any LEDs, and they managed to inject a bit of shellcode, but they needed to dump a copy of the firmware of a Hewlett-Packard graphing calculator. And what they found was that if they jumped to a particular address, it would beep. So they did a long beep for a 0 and a short beep for a 1. The trouble was that the beep was fixed at 1 second long. So they had to leave this running for 2.5 days with the speaker connected to a microphone that was going into audio cassettes, and they couldn't just leave it running in an empty room because they had to swap the audio cassettes. And then in the end, they wrote an Apple II program that decoded it. But in modern days, we don't have to deal with that as much. So if we were to do this as a standalone program, what we would do is we would set up the general purpose I/O pins in the output direction. This is what tells the chip that it needs to assert the voltage on the pin instead of just measuring it. Then the next thing we do is we blink half of them with a steady clock, and then we blink the other half with data. If you've got a bunch of general purpose I/O pins and you don't know which are LEDs and which are not, just don't care. Skip that first step. And then start blinking one of the registers with 55555 times your clock, and blink the other one with AAAAA and your clock. And the result is that half of the LEDs will look like they're solid on. They're just blinking faster than your eyes can see. And the other half of the LEDs will start visibly blinking on and off. And those are the ones that are dumping data. So you tap one of each with the logic analyzer, and then you record it, tell the logic analyzer to interpret it as SPI, and it gives you all of the bytes out. And this allows you to dump the firmware of a chip using preciously few bytes of shellcode. This is what it would look like visually. On the top, you've got the clock register, or the clock LED, and that's just blinking out a regular pattern so you know where each bit begins and ends. And on the bottom, you have the data coming out, and all that does is once per clock cycle, it changes to the output of the bit that you're trying to dump. And because this matches the SPI protocol so quickly, you can take the Saley logic probe or any other decent logic analyzer, and you can use this to dump a copy of all of the firmware. Now, if you want to return into libc, you're complicated by the fact that even though it's there, it's linked and pruned. And there's nothing like system or exec to allow you to run a shell command directly. So what we can do is we can return to the bootloader with privilege escalation. And what I'm going to show you now is that you can even find these privilege escalation gadgets blind because the firmware is so small. You need to know that the gadget will be commonly created by the compiler. So you can't just imagine that some gadget might exist and then hunt for it, because if it doesn't exist, this technique won't work. But if it does exist and is there, then you can easily take control of the stack and extend that into finding all of the gadgets within the firmware image and then combining them individually to see the effects. Now, when you're returning into the bootloader and mask ROM, because this is permanently a part of the chip, we can assume that the attacker knows what's in the bootloader. And this can't be patched or removed affordably, because as the chips are manufactured, they all come with the default mask ROM. So this is an excellent target in that regard, because it's always at a fixed address, its contents is regularly fixed, there are very few revisions of it to reverse engineer, and it's rather small. It also includes at least one command shell that you can talk to externally, either by USB or by a serial port. And it has all the commands that you as an attacker would want to use as soon as you've elevated your privilege. So in the MSP430, this is from C00 to FFF, and it's just 1 kilobyte. You can reverse engineer it with pen and paper in a few hours for the first time and a few minutes after you're familiar with it. It requires the interrupt table as the password, though, and you might not know this. So if you don't know the addresses of all of the interrupts, then you have to use return-oriented programming or a bit of shellcode to drop into it and to elevate your privileges before you do. When you look at the firmware, you'll see that the first thing that it does is it clears register 11. It does this because register 11 is a global variable which has a bit that describes whether the bootloader password has been provided or not. So because this is a global variable containing the password status, if you can just force this variable and then enter the bootloader just a little bit late, then you'll be able to to dump the code, because it will think that you already have proved that you know the secrets inside of the chip, and it will have been unlocked. Now, if you can execute RAM, you can do this in just 6 bytes. You have an instruction that moves FFFF into register 11, setting the requisite bit. And then you do a call to just a little bit late in the firmware. So the bootloader begins at C00. If you enter at C0A, you will have skipped the clear register 11 instruction. But if you can't execute from RAM, then you need to use return into programming, or really just a return to libc that bounces it through a few places before you get there. So what you do is you build your ROP chain, but you don't actually know what's in flash memory. And everything inside of the bootloader is inlined. So you don't have many return instructions, which means you have preciously few return-oriented programming gadgets. So you can build it blind. And here's how you do that. To start things up, we're going to suppose that we have a Stack Overflow bug. Generally, you'll find this by fuzzing, and you'll just wait for the LEDs to blink, indicating that the device is rebooting, and that lets you recognize your crash. We'll also assume that you have a copy of ROM, but that you do not have a copy of flash, which is a common case when trying to rip firmware out of these devices. And we're going to assume that you cannot execute RAM. So the plan of attack is to use the ROM entry point to find the return address offset. So when you get your crash, the crash is happening because at some point the chip is returning and it's popping the wrong value into the program counter. That's causing it to crash. If you can provide a correct value there, you can make it do something other than rebooting. And in this case, what we want to do is we want to make it jump into the bootloader. This is not yet a victory for us because the bootloader has a password, but it tells us that we control the program counter. And it tells us where in whatever string we've overwritten is the pieces that we need to overwrite to control the rest of the stack. After we have that, we're going to move the bootloader address up 2 bytes in memory. By doing this, it's not going to be at the right place for the return, but we're going to take the other word, the word where the program counter goes, and we're going to put random values in there. Or we're going to try every value in order. And when we do this, one of 2 things is going to happen. Either we're going to drop into the bootloader, and if we drop into the bootloader, then we know that wherever the hell it went in memory, after that, it had a return statement, which popped the second word off into the program counter. This lets us search for return statements in flash memory, even though we cannot yet read flash memory. Then once we've found all of these return addresses, if you go just 1 word before them in code, then you get the final instruction of that function. And if you can find one that's a pop R11, then we have a gadget that gives us control of register 11. And I'll show you in a bit how we can do it for more complicated for more complicated chains. Now, this works because the gadget that we need is rather common and rather small. You're not going to be able to build a Turing-complete interpreter using this technique. It also works because we have a very small address space. With only 64K of memory and the minority of that being used for code, the program that we're searching for gadgets is very small. We also have this feedback mechanism in that we can either crash or not crash, and that leaks 1 bit of information out of the chip. In this case, it lets us know whether the thing that we've jumped to has a return statement or not. But you could construct different queries in your stack. So if you constructed your stack to where it would crash in one way or succeed in another way for anything that you can do in the stack arrangement, then that lets you leak a bit out to the host, out to the attacking party. And unlike a PC attack, where you have to go to all sorts of lengths to make sure that ASLR isn't repeated per try, on a microcontroller, the only thing that scrambled up the software we're attacking is that we don't have its code. So as we reboot, everything stays in the exact same place, and whatever was leaked on the prior try is still valid. So on the first end, we use fuzzing to find our stack buffer overflow. And then we just try filling those bytes with our known good return pointer. This is the entry address for the bootloader. So you can see here that in multiple attempts, the offset was slid over. And every one of these would have rebooted the device to its natural firmware, except for the third attempt, which would drop into the bootloader. And on that attempt, we know that the second pair of bytes controls the return pointer. And we can do this blind, and we can do this without a debugger. Now that we control the program counter, we need to figure out the password. But we can't do that. So instead, what we have to do is we have to find this popr11 gadget. And the first stage to that is searching for the return statements, because we know that all gadgets in the ROP chain are going to come just before a return statement, especially when we're trying to move something out of the stack and into a register. So what we do is we move the bootloader, the BSL entry point, the bootloader entry point, just a little bit further in the stack so that it won't be the address that we return to. And then where that address was, the thing that actually is going into the program counter, at that address, we put a value that we just keep incrementing on each try. And we record all of the successes and all of the failures. And every success might be a return instruction. If you have 2 successes in a row, then what's usually happening is that it's a return instruction followed by a leaf function or something that doesn't rely upon anything on the stack. And that's because the leaf function repairs its own stack before it returns. So if you find an address that works, and just before it there's an address that doesn't work, that's a gadget. Now, we have the gadgets, but we don't know what they do yet. But that's okay because there are only 59 of them. In a few different programs for this microcontroller that we tried, there were between 50 and 150 valid instruction words of the program per valid entry point of gadget. This varies drastically by the architecture and the compiler, but for all embedded systems, it's rather low. So the fourth step is to try each of these out with the appropriate stack layout, just shuffling the order up until it works. And eventually, this will drop into the bootloader, and as it drops into the bootloader, we will have already elevated our privilege, and we can then politely ask it for a copy of firmware, and it will read it back to us. The final call stack looks something like this, in that the highest word, that's the last thing that will be popped off the stack, is 0C0E. That's the bootloader entry point, and that's what's called last. Just after that, we have FFFF, which is a constant that we want to be loaded into register 11. And then following that, we have the address of some gadget that pops the stack word into register 11. And because we've narrowed it down to 59 possibilities, after the narrowing down process, we could do it in 59 attempts. If we weren't to narrow it down first, we could do it in 8,000 attempts. If there are 2 gadgets, then it only takes 59 squared, or 4,000 tries. And for 3, we could do it in 200,000 tries, which is still feasibly small to accomplish it in a reasonable amount of time. So you can build these ROP chains even when you don't have a copy of the code, and even when the purpose of the exploit is to get the code out of the chip. Now, on a higher-end chip, you would patch RAM. So, because many of these chips can't execute flash directly, they copy everything into RAM, and then you just patch RAM. This works just like a TSR would in MS-DOS, and all of your traditional hooking functions work. But when you're patching flash, it's different, because there are cases in which you can overwrite flash, but you can't erase flash. This is common when you're trying to patch the interrupt table directly, because all hell breaks loose if the interrupt table is in flash memory. You can't move it and you erase it, because at that point there are no valid interrupts and you've bricked the chip. Now, NOR flash memory does not work like RAM. You can clear bits individually, You can move them from a 1 to a 0, but you can't move them back individually. You can't raise a 0 to a 1 unless you erase the entire page. And erasing an entire page is rather traumatic for the chip, because for that amount of time, everything in that page is now FFFF. And if you're trying to patch a piece of code that contains code that you need to do your write primitive, then you've just bricked the machine as you're trying to exploit it. So what you do is you construct overwrites that turn what used to be there into what you want there only by doing bitwise ands. So as Flash is overwritten, every bit gets pumped up to a 1, and then you're dropping it to zeros. So if you begin with FFFF, and then you write DEAD on top of it, what it's actually doing is inverting DEAD, and then clearing all of those bits. So what remains is DEAD. Now, if you imagine that you start with DEAD, and you write FF00, what happens is that it inverts FF00 to get 00FF, and then it clears that second byte. So you wind up with DE00. So in this case, it's valuable to know which bits to clear in order to change the way that a program behaves. And you can do this with only a poke primitive, because all you need to do is call the regular Flash writing functions. But you can't do an erase as easily as a write, because the erase might damage your poke primitive. So what tricks can allow you to know the right bits to clear? On the MSP430, RAM is beneath Flash. So you can clear significant bits of an immediate address to change the destination of a call instruction to move it from Flash memory to RAM. For example, if you've got a call to BEF, you can move that to a call to 02EF by clearing bits in the upper word. And 02EF is within RAM. So this allows you to move a function pointer to point into a buffer that you control. And then if you do this on an obscure command, you can just move the handler for a command you would otherwise never need to be in RAM that you control, and give yourself a backdoor into the application. This is particularly handy when you're trying to do a simple patch to give you execution from RAM in order to avoid bricking the device. Now in 8051, you can do a similar thing in code memory by knopping out instructions. So 8051 has the particularly nice feature that 00 is a 1-byte instruction that is a no-op. And you can always clear bits. So you could change any instruction byte you want to 00 and turn it into a no-op. This allows you to clear out instructions of code to change its behavior. So if you have a nosy instruction that lowers your privilege before the application boots up, you can just cut out that region of code and everything else will function properly. So we're running out of time now, but I hope from this lecture you've learned that embedded systems are exploited in different ways from host PCs, and that all of these unique and annoying behaviors that make it hard to develop for them can be used in writing exploits against them. Every particular limitation that I've mentioned here has an exception to it. Just as some 8051 machines can execute from RAM, some von Neumann machines cannot. Similarly for everything else here, but it's by recognizing the limitations and the quirks of your particular target that you can come up with an exploit that functions on it. And that functions on it using the minimal amount of space and of development effort. So thank you kindly for your time. Are there any questions?
We have 5 minutes for questions. I'll take this one first, and you will be next. Daniel. Actually, can I, Daniel? I'll get Daniel because he has to run off after this.
So a question is there always a POP R11 gadget on those chips?
No. Pick whatever gadget you want, and it's not always available. Part of the One of the privileges that you have in a larger machine is that you have a much larger call stack. And so you can sort of combine weaker gadgets to build more valuable ones. In the PopR11 example, I had the advantage that the compiler was using that as a temporary variable inside of flash memory, but that the mask ROM was made with a different compiler that used that same register as a global variable. And by this technique of randomly assembling your gadgets, you lose the ability to perform any function, and you're sort of limited to doing the things that your gadgets allow. So I was rather lucky that PopR11 was among the available gadgets.
Yeah, my question is rather, how do you start and find a stack buffer overflow, for example, that allows you to overwrite the return addresses? I mean, on some architectures, the return address is stored in a register, or so in MSP 430 and the Intel 8051. Is it always the case that the return address is stored on the stack, or?
So on the MSP 430, they went with an almost RISC design, but they elected to have return pointers on the stack instead of in a link register, as you might have on, say, MIPS or PowerPC. In the 8051, the compiler can actually choose different ways to manage the return stack. So if you have an application that's expected to do recursive calls, the recursive calling convention will be different from the standard calling convention, and the stacks will actually be in different memories. So like anything else, this is unique to the individual chip that you're attacking. But in general, it's very common for microcontrollers to save their return pointers onto the stack, and for the programmers to be very loose about buffer lengths.
And how would you attack a chip that you cannot find any crashes by fuzzing? And how do you get the code if you don't get running? I mean, if you don't get any vulnerability?
If I only needed to copy the code from one chip, I would call Chris Tarnowski, because that man can break anything with needles.
Yeah, but that's not, I mean, playing by the rules.
Yeah. If you get to the point where nothing else works, there are lab services, or you can call in a colleague. But generally, I've had very good luck attacking these bootloaders.
Okay, thank you.
Any other questions from the floor? No? Travis, thank you very much.
Thank you.